Welcome back to linear algebra. In this video, I'm going to introduce you to the eigenvalue problem. Many mathematicians describe the eigenvalue problem as the reason that linear algebra is so important. And I can't necessarily argue with that claim, although I will mention that there is one other idea we're going to come to a little bit later on in this course, where we work on generalizing the idea of a vector and a vector space. Which I think is a little bit more important. But to be honest, it's a little bit more important because it allows us to take the eigenvalue problem and put it into different contexts. All right. The eigenvalue problem, very simply, asks us to consider an n by n matrix A. All right, so it is important that we have a square matrix A here, although that does actually fall in naturally from the rest of the definition. I want to take a square matrix A, multiply it by some vector, which I'll just call x, and I want to get out a constant lambda times my vector x. All right, so A has to be square for this to work, right? N-dimensional vector times a matrix that is an n by n matrix gives me an n-dimensional vector out. If the matrix was in any other shape, I would get something else out, or the multiplication wouldn't be defined. All right, so A has to be square. And again, lambda here is a constant. Right, so for some lambda in R. And our question, our goal here is asking, are there any vectors for this particular matrix where this actually happens? As a general rule, this doesn't happen, right? If you take an arbitrary square matrix, you multiply it by an arbitrary vector, you usually do not get a constant multiple of that same vector back. So we're looking for what circumstances cause this to happen. And before I get into the algebra of that, I want to start off thinking about this in the abstract. What does it mean to take a matrix times x and get some lambda times x? Well, in other words, what does it mean to take a vector and multiply it by a constant? That is a rule that will talk about the scale of the vector. If lambda is bigger than 1, it will take a vector and stretch it out. If lambda is between 0 and 1, it will take that vector and it will shrink it down. If lambda is negative, it will take that vector and instead of pointing in one direction, it will suddenly be pointing in the other direction. But no matter what happens, you're going to get a new vector along the same line. We call such a value lambda is an eigenvalue of A, and x is a corresponding eigenvector. This prefix of eigen shows up in a lot of contexts related to this. We're going to see in not too far into the future that there are in fact infinitely many eigenvectors for any eigenvalue, but those eigenvectors will form a vector space. So we can talk about the eigenspace, the vector subspace of eigenvectors for a given eigenvalue. If you go onward, depending on the kinds of things you study that build on linear algebra, differential equations and then going on to a branch of mathematics called functional analysis brings the eigenvalue problem up in a different context, where instead of eigenvectors, you have eigenfunctions. Quantum mechanics is based around the eigenvalue problem. And because the things that you're looking at in quantum mechanics are the states of the quantum substance that you're dealing with, they call them the eigenstates, so on and so on and so on. The root word there, which we horribly mispronounce in English as eigen, is from a German word that I'm not going to attempt to pronounce, but is probably something similar to eigen. And the translation comes with the ideas of a characteristic or an ownership or a possessiveness. So the eigenvalues of a matrix are in some way characteristic of the matrix. All right, let's start with a relatively simple matrix. 1, 0, 0, negative 1. And we don't have any algebraic tools for dealing with the eigenvalue problem just yet. All we have is the vocabulary and that picture. The eigenvalue problem is going to look for ways to take vectors and turn them into multiples of themselves in some way, shape, or form. So what does that look like geometrically? What does this matrix look like geometrically? This is kind of backwards of something we've done before, but we learned that we could build up a matrix to represent a transformation by mapping out what happens to each of the basis unit normal vectors. So in this case, this matrix has the property that it's going to take 1, 0 and map it to 1, 0, just the first column. And it's going to take 0, 1 and map it to the second column, which in this case is 0, negative 1. And for a vector somewhere in between, it's going to do something in between, which is not all that helpful. But this right there gives us what we want. Right? If I replace that arrow with multiplication by matrix A times the matrix 1, 0 is 1 times 1, 0. And A times the matrix 0, 1, matrix A times the vector 0, 1 is the negative of, or negative 1 times 0, 1. So thinking about the geometry, thinking about the physical nature of these vectors gives us an immediate way of representing what's going to happen. This is a very much contrived example. As a general rule, this kind of thing doesn't help, but in this particular case, it does. While we're looking at this matrix, let's think about physically what this is doing. 1, 0 maps to itself. A vector pointed along the x-axis stays where it is. 0, 1 maps to 0, negative 1. a vector which is pointed along the y-axis gets flipped upside down. And if you are a vector anywhere else, you are going to get mirrored. The x component is going to stay the same. The y component is going to get flipped upside down. That's going to take any other vector out of the line that it was in and put it onto a new line. Its reflection specifically, but a different line is all that matters to us. If we look at this in any other matrix, that kind of analysis just doesn't work anymore. So if I consider the matrix 3, 1, 1, 3, I know as a transformation that this is the matrix that takes 1, 0 and maps it to 3, 1, and takes 0, 1 and maps it to 1, 3, right? Doing the same thing I did before. Multiplication with the matrix takes the standard basis vectors and maps them to the columns of the matrix. But 3, 1 is not a multiple of 1, 0, and 0, 1 is not a multiple of 1, 3. I claim that the vector 1, 1 is an eigenvector of A. How did I get that? Well, we'll answer that question a little bit later on. For right now, that's one extra piece of information you are being handed. I claim that 1, 1 is an eigenvector for this matrix. To see if that works, let's set up the multiplication. All right, multiplying row dot with column. So 3 times 1, 1 times 1, 3 plus 1 is 4. Second row, we have 1 plus 3, which is also 4. And 4, 4 is definitely 4 times 1, 1. All right, so 1, 1 is an eigenvector of this matrix, and that eigenvector has a corresponding eigenvalue of 4. One of the interesting things about the eigenvalue problem is that if you have an eigenvector and you multiply it by anything, you have a new eigenvector for the same eigenvalue. Right? If I just multiply both sides of this equation by 3, we can see that a little bit more specifically here. Remember that 3 times 1, 1, and let's do 5 times. 5 times 1, 1, which is the vector 5, 5. Right? Again, for right now, this is information I'm giving you. We'll get to how to figure out that first piece of information a little bit later. But I claim that 5, 5 must also be an eigenvector with the same eigenvalue of 4, because this is a multiple of an eigenvector we've already found. We can check that by multiplying 3, 1, 1, 3 times 5, 5. Right? 3 times 5 is 15. 1 times 5 is 5. 15 plus 5 is 20. And then multiplying the second row, we get 5 and 15, which is also 20. And I could factor out a 20 if I wanted to, but my goal is to get it to look like 5, 5 again. So I notice that if I factor out a 4, it leaves behind 5, 5. Right? So if I have something that I know is an eigenvalue, I'm sorry, if I have something that I know is an eigenvector, I can multiply the matrix times that vector and figure out the corresponding eigenvalue. If I have one eigenvector, I can find another eigenvector for the same eigenvalue by multiplying the eigenvector by a constant. Any and every constant works. So with that idea in mind, let's go ahead and define the eigenspace of matrix A corresponding to eigenvalue lambda. Um, I could just describe this as the set of all eigenvectors, but it's also the span, which gives us one more piece of information. Given eigenvalues, or given eigenvalues and eigenvectors for that eigenvalue, a linear combination of those is also an eigenvector. And that makes sense. The proof here isn't too bad. Let's assume that we have two eigenvectors, x1 and x2. Because they are eigenvectors, they satisfy the eigenvalue problem. ax1 is lambda x1, ax2 is lambda x2. Now, a matrix can have multiple different eigenvalues, but I am emphasizing here that I'm using the same eigenvalue for both of these eigenvectors. Then if I take a linear combination, c1x1 plus c2x2, I can take advantage of the distributive property of matrix multiplication and the associativity with scalar multiplication. And this is C1 times AX1 plus C2 times AX2. And of course, AX1 is lambda x1 and AX2 is lambda x2. And I can factor out the lambda to get C1 x1 plus C2 x2. All right. So as we go forward, some things we'll be looking at later on. We're going to be looking for ways to get a linearly independent set of eigenvectors which is going to give us a nice basis for an eigenspace. And we're going to look at matrices that have multiple eigenvalues and an eigenspace for each eigenvalue instead of just an individual eigenvector. But for right now, I'm just looking at the idea of the eigenvalue problem in general and kind of previewing some of the things we want to do with it as we move onward. All right, so if we know the eigenvectors, finding the eigenvalues is fairly straightforward. If we want to go the other direction, if we know an eigenvalue, we can find an eigenvector, but that's a little bit more involved. Still doable, just a little bit more involved. All right, so let's take a look at this matrix. 1, 2, 4, 3. I claim that lambda equals 5 is an eigenvalue of this matrix. And in order to verify that, I need to find a vector x such that a times x is equal to 5x. All right. Now that is an equation. It is an equation that we can, in theory, solve by rewriting it as a system, right? I'm going to go off to the side and I'm going to write this out, although you may not want to copy it down because it's not valuable in the sense that it doesn't extend nicely into higher dimensional situations. But I can take my matrix 1, 2, 4, 3. I can multiply by my vector, which has components x1, x2, and get 5 times x1, x2. I can actually perform that multiplication. And I can turn that from a vector equation into a system of equations. x1 plus 2x2 equals 5x1. 4x1 plus 3x2 equals 5x2. Although that's not a very common way of writing out something like this. So maybe I should rearrange by subtracting the right-hand side and getting this equal to 0. Right? x1 minus 5x1 is negative 4x1 plus 2x2 equals 0. On the second equation, I have 4x1, and then 3x2 minus 5x2 is minus 2x2 equals 0. And so we can take this linear system, turn it into a system of equations as a homogeneous system of equations, and I get the exact same equation twice. The fact that it's the exact same equation twice actually isn't uncommon. That's pretty normal. I could choose either one of them and solve, right? Just take the first equation and multiply by negative 1 on both sides, you get the second equation. That's what I mean when I say we get the same equation twice. I could choose either one of those equations and I could solve, and that would give me the vector that I need. But like I said, I want to try to generalize this. I want to try to explain what happened here. we took and we moved the eigenvalue from the right side to the left side by subtracting it. And to show you how to do that in general, I'm going to come back to my matrix version of this linear system, and I'm going to introduce an extra matrix, the identity matrix I. Because we can multiply any vector times the identity matrix and it doesn't change that vector at all. And then I can subtract to get this set up as a homogeneous system. And I can factor out to get a minus 5i all times x is equal to 0. In this particular case, going through and doing that doesn't really save us all that much, because if I put in a minus 5i, well, that's 1, 2, 4, 1 minus 5 times 1, 0, 0, 1, which is 1, 2, 4, 1 minus 5, 0, 0, 5, or negative 4, 2, 4. Oh, that's what I did wrong. That was supposed to be a 3, and I wrote down a 1. Sorry about that. And that will take me back to the same linear system I had before. All right, so does it actually save us anything? Yes and no. As we get to more complicated looking matrices, as we go beyond the 2 by 2 and into the 3 by 3, 4 by 4, and even higher cases, things like this are going to make our lives easier. But in general, I have that x1 is equal to 1/2 of x2, which I can set up fairly simply, pick some value for x2. I want it to be an even number, so I can take that half nicely. So let's call it 2t. And then half of 2t is just t. And that is the span of a single vector. Right? If I factor the t out and write this as t times the vector 1, 2, that gives a better picture of what's happening. Right? As we said before, any linear combination of eigenvectors are also eigenvectors. 1, 2 is an eigenvector. So is 2, 4, and 3, 6, and square root of 3, 2 square root of 3, and anything else you might want to use. All right, but the important thing here is we were able to play around a little bit and think about the algebra. We were also able to, we were also able to find the eigenvector, or the family of all the eigenvectors, which correspond to that eigenvalue, right? Any multiple of 1, 2 is the span of vector 1, 2. So that is the eigenspace. 1, 2, a single vector, which is not the zero vector, forms the basis for a one-dimensional vector space. So we can describe that as the basis. We can describe the eigenspace as being one-dimensional. We've got a lot of really great results from a relatively simple problem. Let's take a look at one more like this before we wrap up. I've been looking at 2 by 2 matrices. Let's do at least one that is a little bit larger. for the matrix 7, 1, negative 2, negative 3, 3, 6, 2, 2, 2, I claim that 6 is an eigenvalue. It's likely not the only eigenvalue, but I claim that it is an eigenvalue, and I want to verify that by finding the eigenspace. As we saw in the previous problem, it's going to be convenient if we take A and subtract our eigenvalue lambda multiplied by the identity matrix. In this case, we are looking at 7, 1, negative 2, negative 3, 3, 6, 2, 2, 2, minus. And multiplying the identity matrix by a constant is pretty easy. 1 times anything is that thing. 0 times anything is 0. So we get a couple of 6s and a whole bunch of 0s when we do that. And then performing the subtraction. 7 minus 6 is 1. 1 minus 0 is 1. And negative 2. Negative 3. Negative 3. 6. 2. 2. Negative 4. This is a computation you're going to do often enough that you'll realize that you can do it without having to write everything down relatively quickly. All right, so this is the matrix that we want to find the null space for. We want to find the set of values where if we take this and multiply it times x, we get 0. So I'm going to take this matrix and I'm going to augment it, putting the 0 vector in, and then I'm going to solve the system using Gauss-Jordan elimination. This one is actually very straightforward in that regard. If I take row 2 plus 3 times row 1, and I take row 3 minus 2 times row 1, well, negative 3 plus 3 is 0. Negative 3 plus 3 is 0. 6 minus 6 is 0. 2 minus 2 is 0. 2 minus 2 is 0. Negative 4 minus negative 4. Negative 4 plus 4 is 0. And we get one non-zero row and 2 rows of all zeros. Right, so I get just one equation out of this. X1 plus x2 minus 2x3 equals 0, which I can rearrange and write as x1 equals negative x2 plus 2x3. All right, so x2 and x3 are not leading variables. They don't correspond to a leading entry in a row. So I'm going to need some parameters. I'm going to choose S for x2 and T for x3. And then x1 is minus x2, which is S. So minus S plus 2 times x3, which is now T. And just regrouping this, I have S times negative 1, 1, 0 plus T times 2, 0, 1. Right, we get the span of these two vectors. These two vectors are linearly independent. If you would like to take the time to prove that to yourself, I encourage that. But the fact that they are linearly independent is good enough for us for right now. This is a two-dimensional vector space. We have two basis vectors. But again, the thing that is important, the thing that I was asking about here is just, can you find eigenvectors? And we found the description of all the eigenvectors, so we're happy. So here is another matrix, 0, 1, 0, 0, 0, 1, 4, negative 17, 8. I claim that 4 is an eigenvalue for this matrix. I would like you to find the corresponding eigenspace. All right, so take a couple of minutes, see what you can do with that one, and I'll see you in the next video.